A rocket is not mostly payload. It is not even mostly machine. It is mostly fuel. And the strangest part is this: much of that fuel is there to lift other fuel. That sounds like bad design, but it is not. It is the rocket equation. A rocket survives by throwing mass away. But before that mass can help, the rocket must carry it. So the thing that saves the rocket is also the thing that makes the rocket heavy. Fuel lifts fuel. The equation we are going to earn is delta V equals V sub E times the natural logarithm of m0 over m final. By the end, this line should feel less like a formula and more like a warning. Before a rocket is designed, the mission gives it a bill. Speed up here, turn here, raise the path here, correct the path here, slow down here. Each item is a required change in velocity. Add those items together and you get the rocket's delta V demand. Delta V is not distance. It is not exactly speed. It is the total change in motion the rocket must buy. Distance can often be crossed by coasting. Changing velocity is what costs fuel. Imagine a skater on almost frictionless ice. Once the skater is gliding, they can coast. But to change motion, they must throw a ball. Throw one backward and they speed up. Throw one forward and they slow down. Throw one sideways and their path turns. A rocket is not a skater. It does not push against ice, air, or space. It changes motion by throwing fuel mass backward as exhaust. So the mission demands delta V. The rocket must supply it. If a rocket doubles the fuel it carries, should it double the delta V it can produce? No. Fuel has two lives. After it burns, it becomes exhaust, and that helps. Before it burns, it is mass, and that hurts. The rocket must accelerate the fuel that has not yet been burned. Now look at three ideal rockets. Same engine, same final mass, only the starting mass changes. Rocket A starts twice as heavy as it finishes. Rocket B starts 4 times as heavy. Rocket C starts 8 times as heavy. Which one gives twice the delta V of Rocket A? Rocket B. But notice what happened. To double that delta V step, the mass ratio did not add from 2 to 3, it multiplied from 2 to 4. To add the next same step, it must multiply again from 4 to 8. This is the shape of the problem before we even write the logarithm. Now let us earn why that shape appears. At one instant, a rocket has mass m and velocity v. Then it throws away a tiny amount of fuel as exhaust. Call that tiny thrown away mass d mu. Here, d mu is positive. It means mass that has left the rocket. After the throw, the rocket is a little lighter, m minus d mu, and it is moving a little faster, v plus dv. The exhaust has been thrown backward relative to the rocket with effective exhaust velocity v sub e. So, from the outside, that tiny exhaust mass is moving at about v minus v sub e. Now use momentum accounting. Momentum before equals momentum after. Before the throw, the rocket's momentum is mv. After the throw, there are 2 pieces to count. the remaining rocket, and the exhaust. So the momentum balance is this: mv equals m minus d mu times v plus dv plus d mu times v minus v sub e. This looks heavier than the idea underneath it. Expand it, and the large ordinary motion cancels out. What remains is the small exchange that matters. M times dv equals v sub e times d mu. In words, the rocket's tiny gain in forward momentum matches the backward momentum carried away by the exhaust. So the tiny velocity gain is dv equals v sub e times d mu divided by m. This is the heart of the rocket equation. A tiny amount of thrown away fuel gives a tiny velocity change. A faster exhaust gives more change. A heavier rocket gets less change from the same thrown away fuel. When the rocket is heavy, does 1 kilogram of fuel help more or less? Less. The same thrown away mass gives less velocity change when it must push a larger remaining rocket. That is why the current mass m sits underneath the fraction. Now repeat the tiny throw again and again. But the rocket is not the same mass throughout the burn. Every time fuel leaves, the rocket becomes lighter. So later fuel throws act on a smaller rocket. The starting mass is m0. Payload, structure, engines, tanks, and all fuel before the burn. The final mass is m final. What remains after that burn? The ratio m0 over m final is the mass ratio. Fuel thrown away is mass lost by the rocket, so d mu equals negative dm. Substitute that into the tiny step equation. dv equals negative v sub e times dm over m. Now add every tiny velocity gain while the mass slides from m0 to m final. The left side becomes total delta v. The right side adds 1 over m over changing mass. And the result of adding 1 over m over changing mass is a logarithm. Delta v equals v sub e times the natural logarithm of m0 over m final. That logarithm is not decoration. It appears because the rocket gains velocity while its own mass is changing. Now the visual experiment makes sense. A logarithm turns multiplication into addition. If the mass ratio doubles from 1 to 2, that gives 1 step. If it doubles again from 2 to 4, that gives another step. From 4 to 8, another. Equal multiplications of mass ratio become equal additions of delta v. Use a rounded teaching value. Let effective exhaust velocity be about 3 kilometers per second. Then each doubling of mass ratio adds about 2.1 kilometers per second of ideal delta v. Mass ratio 2 gives about 2.1. Mass ratio 4 gives about 4.2. Mass ratio 8 gives about 6.2. Mass ratio 16 gives about 8.3. The mass ratio is multiplying, but delta v is adding. If a rocket needs about 9 kilometers per second of ideal delta v, is a mass ratio of 10 enough? No. At this exhaust velocity, 9 kilometers per second needs a mass ratio of about 20 to 1. If the final mass is 10 tons, the starting mass must be about 200 tons in this ideal calculation. Most of the difference is fuel, and this is before real losses are added. Turn the equation around and the warning becomes sharper. To demand more delta V is to demand exponentially more mass ratio. That is the tyranny of fuel. Not that fuel is useless, fuel is essential, but fuel must be carried before it can be thrown away. Now look from the top of the rocket. Imagine adding 1 extra ton to the payload. 1 ton sounds small, but that extra ton must be carried by the stage below it, so that stage needs more fuel. But the extra fuel also has mass, so the lower rocket must carry the extra payload plus the extra fuel, plus the structure needed to hold that fuel. The penalty travels downward. A small increase at the top can become a much larger increase at the bottom. A kilogram saved near the payload is not merely 1 kilogram saved. It can prevent many kilograms from being added below. This is why rockets are divided into stages. A single rocket has to carry empty tanks and engines even after they have finished their job. Staging removes dead weight. After one stage burns, the rocket drops that stage. The remaining rocket no longer has to accelerate those empty tanks and engines. Staging is not a trick against the equation. It is obedience to the equation. Now protect the equation from misuse. This equation is an ideal model. It assumes ideal impulsive burn, effective exhaust velocity, no gravity losses, and no drag losses. Real mission budgets add those losses. So it does not tell the exact final speed of a real rocket rising through the atmosphere. It tells the ideal velocity change capability produced by exhaust velocity and mass ratio under stated assumptions. The clean model is powerful, but clean does not mean complete. Historically, this should not be told as one person inventing rocketry alone. The equation is usually associated with Tsiolkovsky because he applied it to rocket travel beyond Earth. Earlier work on rocket motion existed. Later engineers, experimenters, and institutions turned the relation into working machines. The equation did not build rockets by itself. It gave designers a severe accounting truth. So return to the opening. Why is a rocket mostly fuel? Because fuel has two lives. Before it burns, it is burden. After it burns, it is exhaust. The rocket must carry the fuel that will later help it. Then it must carry the fuel needed to carry that fuel. The equation compresses that loop into one line. Delta V equals V sub E times the natural logarithm of m0 over m final. A rocket buys changes in velocity by throwing mass backward. Ideal delta V grows with exhaust velocity and with the logarithm of mass ratio. So every equal multiplication of starting mass adds another step of velocity change. But the mass required for larger delta V grows brutally fast. That is the tyranny of fuel. Not that fuel is bad. That fuel must be carried before it can be thrown away. For more great equations opened in this way, subscribe to QuestionKind.